In this problem, we have two masses, m1, and we also have m2. m1 we can see is bigger, and m2 is smaller. Our task is to find how far from m1 to place a third point mass, m3. Hang on, let me draw m3. Okay, where should I place it? How far from m1? Should it be this far, this far, this far? Where should it be placed? Well, what are we trying to do? We want the net force on m3 to be 0. So what forces act on m3? Because m3 has mass, it's attracted to the other two masses. It's getting pulled to the left by m1, and it's attracted toward m2 as well. But this force is bigger, and that one is smaller, because Newton's equation for gravity says if you have a big mass, m1 is big, you feel a bigger force. If you have a smaller mass, the force between m2 and m3, if you have a smaller mass and m2 is smaller, then that force will be weaker. So I can't put it right in the middle, otherwise m1 wins out and the forces are not equal. Wait, why do we want the forces to be equal? Oh yeah, we want the net force to be 0, so those values have to cancel each other out. And right now, this is bigger. What do I have to do then? Where do I have to put m3 to make the two forces cancel out? Should I go closer? No! If you decrease the radius, the distance, then you decrease the denominator and you'll have an even bigger force. So, okay, what should we do? We need to go farther away from the big mass and closer to the little guy. Let's draw those forces again, and let's assume we've reached the point where they are equal. I'll call this force the force of 1, mass 1, pulling on our green little guy. And I'll call this force the force of 2 pulling on our green little guy. There's mass 2. We know some other things. They told us the distance, the total distance from 1 to 2. That's 20 meters. And let's label some other distances. From 1 to 3, I'll call that R1, 3. From 2 to 3, can you guess what I'm going to call that? Oh, you guessed it, R2, 3. Okay, these are distances, those arrows are forces, and we've placed we've placed M3, the green little guy has been placed so that those forces perfectly cancel. So we know this. What else do we know? Well, if we look at our distances, R1, 3 plus R2, 3 equals the total. Let's write that down. R1, 3 plus R2, 3 equals 20 meters. And we're looking for how far, let's read it again, how far from M1 is M3 placed? In other words, we're looking for this distance. Our unknown is, let's write this over here. The distance 3 should be placed from mass 1. So R1, 3 is our unknown. Leave that up. Okay, how do we solve? We start right here. The forces cancel out, so they're perfectly equal. If we plug in with Newton's law of universal gravitation, this is the force between 1 and 3. We divide by the distance between them. The right side is the force between mass 2 on mass 3. And we divide by the distance between those. Squared, of course. Can we simplify? Yes! Look at this. The g's cancel. The m's cancel, and we know the values m1 and m2. Let's write those in. This m1 they said was 49, and m2 they said was 8. Okay. So where are we? Are we any closer to a solution? Please let the answer be yes. Yeah, we're way closer to a solution. Here is an equation with two unknowns. Here is a second equation with the same unknowns. We have a system of two equations with two unknowns. So my preference, we're trying to find R13. My preference, isolate R23, get some expression, and then plug that expression in, substitute in, right here, and solve for our single unknown. That's my approach. Here's how that goes. Okay, first thing we can do is we can cross multiply, get those unknowns out of the denominator. I have 49 R23 squared equals 8 R13 squared. Whoops. What happened to my squared? Has that been gone the whole time? Thanks. Then we have to square root both sides. That's going to help. Just like when if you have 1/2 v and you square it, you have to distribute the squaring. The same thing is true here. You have to distribute the square rooting to both of the factors. So square root of 49, that's 7. The square root of this squared is just R23. The square root of 8, apply it the same way, distribute the square root to everything inside the parentheses, everything under the radical. Square root of 8 is, carry the 2, don't forget to square. I cheated, there it is. It's 2.828. And when I square root this, the square root cancels out the square. And I end up with just R13. Next, I'll divide both sides by, what am I trying to isolate? This is my unknown, so I have to plug in something for R23. So let me isolate R23. Here it is. I divide both sides by 7. And what do I get? 0.404 times R13. Let's plug that on in. What was it? R23 is equal to 0.404 times R13. But you can think of it like 1 R13 plus 0.4 R13. That's like saying 3x plus 1x. That would come to 4x, right? Let's do the same procedure here. Factor out an R13. You have 1 plus 0.404. 1 plus 0.404 is 1.404. R13. Divide both sides by 1.404, and you are finished. So let's do that. 20 over 1.404, and I think it was 06 if we keep an extra couple decimal places. 14.2. That's how far the mass should be placed from M1. That is this distance. And that is your answer. Let's really briefly recap the entire procedure. We started by adding the distances to get the total. Then we equated the forces on mass 3. Next, we substituted into those forces using Newton's law of gravitation. We simplified, and we substituted in M1 and M3. Oops. M1, we plugged in the value. M2, we plugged in the value. We said R13 is the unknown, so find some expression to plug in for R23. We isolated R23 to get that expression. We substituted in to eliminate or get rid of R23, and we solved for the unknown. That's how you solve these problems. Well done, high five your neighbor, and thanks for watching.